Oh, just a reminder, you do have that quiz out there from yesterday. I believe it's quiz 4-10. Make sure you get that completed and submitted here as soon as you can. Um, we left off yesterday, we were talking about applications of trigonometry and making cuts and stuff like that. So what we want to look at today is a rafter. If I need to cut any sort of a hand-framed rafter, let's say I know that my slope is a 512 slope. I want to know what angle to make this cut here at. So if I'm going to run it, let's say I'm going to run it through a table saw. We have our blade on the table saw. I need to know as I run my guide through what angle to set that guide at. So this is a 512 slope, which means the 512, the slope of the roof, actually gives me this angle right here. It's a rise of 5 for a run of 12. And of course, that is a right angle there because we're dealing with horizontal and vertical dimension. So to find this angle here, I'm just going to call it theta for now. What I have, the 5 is the opposite side, and the 12 is the adjacent side. The trig function we have that uses opposite and adjacent is the tangent. Tangent of the angle, of any angle, is the opposite side over the adjacent side. Well, here I do not know the angle. I'm going to just leave the theta in there for that. But I know the opposite side is 5 and the adjacent side is 12. So now I am missing the angle. I am looking for a missing angle. And whenever that's the case, whenever we are looking for a missing angle, we solve this. We solve this by using the inverse trig function. So if I do an inverse tangent, it's going to cancel out the tangent, leave me with just the angle theta equals the inverse tangent of 5 divided by 12. So we'll punch this in the calculator. Second tangent, 5 divided by 12, close parentheses, and at 22.62 degrees. So this angle right here is 22.62 degrees. However, that is not the angle right here, the angle that I'm looking for. That angle, now, again, depending on how your table saw is calibrated, if it is set so that this is marked at 0 degrees, yes, you would just turn it 22.62 degrees off to whichever side you're going to use, and that would be the appropriate angle. But what if I want this angle right here? That angle, of course, this would be a right angle here, still vertical and horizontal dimensions, is going to be the complement of the 22.62. So if I subtract, that ends up being 67.38 degrees. Is that angle? Which, of course, that should be the same. Any rafter like this cut where these ends are parallel ends up being a parallelogram because these sides are parallel as well. And remember, one of our rules of a parallelogram is the opposite angles are the same. So if this one here is 67.38, this one up here is also 67.38 degrees. We just found that 22.62 degrees goes with a 512 slope. So let's say we are sheeting a gable end. And I'm going to leave the overhangs off here just to simplify this. And I've just done a row of sheeting across here, and that comes out, well, let's say that we are 14 inches below this corner here. What that means is to put a piece of sheeting up here, I'm going to need to start right here, 14 inches above that corner, and cut it like that. I need to know, in order to draw my line, where this point here is located. So my right triangle here is the piece that I am cutting off of my piece of sheeting. So that is my right angle. This then is my right triangle. At this point, I know one angle of that right triangle. That's this angle right here is the 22.62 degrees. When we are looking at these slope angles, we talked about angles of elevation and angles of depression. An angle of elevation is if you are standing on a flat surface, a flat ground, and you are looking up at something. Your angle of elevation is this angle right here. Well, if you think about that being a roof slope, that's exactly what it is. If this were the flat ground, the angle of elevation that you're looking up is that angle right there. That is the 22.62 degrees from the slope of our roof. Well, if I were to switch this around, and if I were to go to stand up here somewhere and look back down to that point, the angle of depression is the angle from the horizontal down to my line of sight. Those two angles will be the same because it's the same line of sight. I'm just looking at it from the opposite end. So the 512 slope is technically telling us that this angle is 22.62 degrees. But coming down from the top, this angle up here must also be the same angle, the 22.62 degrees. This is an angle of elevation. This is the corresponding angle of depression coming from above. So either way, we have that one angle. We need to know a side of this triangle. Well, we can find this side here because we know a standard 4x8 piece of sheeting, this is 4 feet or 48 inches. If I subtract my 14 inches that I need to leave there, 48 inches minus 14 inches makes this dimension 34 inches. Now, I like to draw the triangle away from the situation just because for a lot of people, it's way easier to decode a right triangle if it's by itself. So this side over here is 34 inches. This angle over here was 22.62. To locate this point here, what I really need to know is the length of this side. Well, here we would have the 34 would be, according to the 22.62 degree angle, the 34 is the opposite side. This missing side here is the adjacent side. I'll call that side A for now. We have opposite and adjacent, which once again is tangent. Tangent of an angle is the length of the opposite side over the length of the adjacent side. Here I do know the angle. The angle is 22.62 degrees. My opposite side is 34 inches. My adjacent side is side A. That is what I am looking for. This over 1. And since I'm looking for a side, I make it into a proportion. That's why I put it over 1. And then I cross, multiply, and divide. So it'll be 1 times 34, which is just 34, divided by the tangent of 22.62 degrees, giving us 81.599 inches. Now, 81.599 inches is not a terribly useful measurement. So we're going to keep the 81, and we're going to take that 0.599, so I'm going to subtract the 81 off of here. So we got the 0.599458, blah, blah, blah. And I'm going to go times 16 to turn it into sixteenths. 9.59 would round up to 10 sixteenths, or 5/8 of an inch. So we would go 81 and 5/8 inches from the corner to that spot to mark that, to cut it across that angle. Any questions so far? So when we're working with these applications of right triangles, we need to find right angles in our situation. And of course, from the right angles, we'll construct triangles around them. So we'll find right triangles from those right angles. One of the strategies that we have found for finding those right angles, or anything that's going to be perpendicular, is vertical and horizontal lines. We know that any time a vertical and a horizontal line come together, which is what our slope here is, the slope is the 5 is vertical, the 12 is horizontal. We know that has to form a right angle because those are vertical and horizontal dimensions. Where they meet is perpendicular, is a right angle. We also have preset angles. Like here, we know that a piece of sheeting, that the corners are right angles because that's the way it's manufactured. Or up here, we know that before we cut this, the end of that board was a right angle because that's how it's created. That's how it is manufactured. Well, another application is the radius of a circle to a tangent. And let's take a look at this type of an application here quick. I'm going to be smart and draw my circle first.
Yeah, can you go back up to that for a second, please?
Yep, there you go.
All right, Todd.
You got her? Okay. So there are other things that we'll run into, but those are the three main ones. So now let's look at that application of the radius of a circle to a tangent. We talked about this briefly the other day. Let's say you have a dowel and you need to flatten one side of the dowel. So you're going to set it up in a V block like this to hold it so that you can then use a router or whatever to take a section off of it. Or you might even use a mill if you wanted to take a piece off the top. But in this situation, let's say that we know this dimension here is, well, let's say it is 3/4 of an inch. I'm going to give you an angle here, 54 degrees. We're going to say that our round stock here has a diameter of 1.8 inches. And let's say that this overall height here is 2.8 inches. What I want to find is a dimension x here. How far is that dowel sticking up above the top of this V block. So finding missing dimensions like this, there are two strategies. One possible strategy is to add up smaller dimensions. So that would be if we had smaller pieces. If there were smaller pieces that made up this dimension, we would find those smaller pieces and we would add them all up to get x. That's not the case here. Our second strategy is to subtract dimensions. This is kind of like when we were finding areas of pieces. We could either cut it into smaller pieces and add them together, or we could fill in the missing spots, find the big area, and then subtract out the missing parts. In this case, we're going to use that second strategy where we're going to find this big dimension here, which I'm going to call y. And if I subtract the 2.8 from that, the difference has to be x. Now to find y, I'm actually going to use that first strategy. For y, I know that we have one piece from here to here, which is the 0.75 inches. I know that from the center of this circle up is 0.90 inches. How do I get that? Well, if the diameter is 1.8, the radius is 0.9. So I need to find the rest of this from here to here. To find that, I'm going to construct a right triangle. And to do that right triangle, I have a circle with a tangent to it. So I'm going to draw a radius to that point of tangency. This is where the tangent touches the circle. So when I draw the radius to that point, it forms a right angle with that tangent. I know that radius is 0.9 inches. All the radii of that circle are 0.9 inches. The other thing we know from our last unit is if I connect the center of a circle to where two tangents intersect like that, because it's tangent over here as well, it cuts everything in half. This angle here gets cut in half. So instead of 54, half of 54 is 27 degrees. I'm going to draw this off to the side now. I have this triangle here. So this is the right angle. This is 0.90 inches. And this is 27 degrees. I'm going to call this dimension over here B because that's what I'm trying to find. According to my angle, my 27 degree angle, the 0.9 is the opposite side. B is the hypotenuse, so it doesn't really matter what angle I'm looking at there. So I have opposite and hypotenuse here. The trig function that deals with that, the sine of an angle is opposite over hypotenuse. So if I fill in the information I know that my angle is 27 degrees. My opposite side is 0.90 inches. I'm looking for B, my hypotenuse. Since I am looking for a missing side, I make this into a proportion and I cross, multiply, and divide. So I put my trig function over 1, and I will cross multiply. 1 times 0.9 is 0.9, divided by the sine of 27. 0.9 divided by sine of 27 degrees. 1.982 inches. So this is 1.982 inches. That means over here, this is 1.982 inches. So y is found by adding up those three dimensions. Now we are assuming that the 0.9 and the 0.75 are exact numbers so that I can get away with putting a 0 on the end of them and it doesn't affect it. Otherwise, I would have had to have rounded my 1.982 to just 1.98. I wouldn't have been able to put the 2 on there. But we're going to assume those are exact numbers. So if we add this up, we've got 2, 13, 6, carry the 2, 3.632 inches is that overall height. Which means the height X sticking up here is the difference between the 2.8 and the 3.632. Giving us 0.832 inches. So that piece of round dowel or whatever round stock it is, 6.832 inches above that B block that we're holding it in. Okay, so I want to look at some more applications here. I want to tell you that's a 90-degree angle there. Tell you this is 73 degrees. I'm going to tell you this is 122 feet. 200 feet. This is 170 feet. I want to find this dimension, X here, the length of this side. So as we look at this, it becomes apparent that we're going to have to create right angles. We have this right angle here. One of the possible strategies of creating right angles, by the way, is to create rectangles. When you create rectangles, you know that the sides are perpendicular or parallel, depending on whether it's adjacent sides or opposite sides. I'm going to draw this in over here, parallel to this side over here, knowing that since this is a right angle, this is also a right angle on both sides. I'm going to do the same up here. I'm going to draw in this side parallel to this side, knowing that has to be a right angle there then. So what I have created here is a rectangle, but that rectangle has right angles. Now this also kind of falls in that category of doing horizontal to vertical sides as well. So up here, I can find this length, because I know this is 122 feet up here. One of the powerful things about using a rectangle is the opposite sides of a rectangle are the same. So I know this is also 122 feet, which makes this side up here 170 minus 122, or 48 feet. So we drew in all those rectangles for two purposes. One is to get the right angles. The other is to be able to transfer those dimensions so we could find that length. So now we have this triangle up here. I'll redraw it over here, where we have a right angle, we have a 73-degree angle, we have a 48-foot side. I can find both of those sides, A and C, if I would like to. I don't see where C is going to do me any good. I want to find side A. Side A, according to the 73 degrees, is the opposite side. Look at what I know. I have 48. That would be the adjacent side. So I have opposite and adjacent here. That's a tangent. Tangent of theta is equal to the opposite side divided by the length of the adjacent side. Well, I know my angle is 73 degrees, so I put that in for theta. My opposite side, that's what I'm looking for. That's side A. My adjacent side is the 48 feet. So once again, I am looking for a missing side. So I make it a proportion by putting the trig function over 1. And I will cross multiply and divide. Well, this is tangent of 73 degrees times 48 feet divided by 1. Tangent 73. Make sure you close the parentheses so the calculator doesn't multiply that by 48 before it does the tangent. Times the 48. Now, we don't really have to put in the divided by 1, but I'll do it just to finish it off. We get A is 157.0009 feet. I'm comfortable calling that just 157 feet. For those of you that are wondering, well, why could I round it to 157 feet? Well, let me show you. We'll subtract 157. Oops. Okay, so it's turning into scientific notation. Turning that into inches, I'm going to multiply by 12. Notice it's still 0.01 inches. So it's not an inch. I'm going to multiply that by 16 to get 16ths. Well, it's 0.177. That is not even half of a 16th, so it would round down to 0.16. So yes, that difference, what we rounded off there was less than a 16th of an inch, way less than a 16th of an inch. But that is 157 feet. So this is 157 feet right here, which means this piece is 157 feet. Which means we can now find this piece here as the 200 feet of the whole thing minus 157, which gives us 43 feet. So I have this triangle here. I'm trying to find the hypotenuse of it, x. I have that this is 43 feet, and this is 122 feet. To find x, well, it's still trig, but I don't need to use any of my trig functions. It's just a squared plus b squared equals c squared. So we'll call this a, b, and c. So a squared is 43 squared, plus b is 122, that'll be squared, equals c, which is just x, so it's x squared. So this is the square root of 43 squared plus 122 squared is going to give us x. Giving us 129.356 feet equals x. So once again, that's 129 feet. We'll subtract off the 129. Multiply by 12 to get inches. That'll be 4 inches. Subtract off that 4. Then multiply by 16. You get 4/16 or 1/4 of an inch. So 129 feet, 4 1/4 inches is what that comes out to be. So there's a case of just drawing in auxiliary lines. These lines weren't here. We had to put them in to create right triangles and to create rectangles. The rectangles, like we said, help us create right angles, but it also allows us to transfer dimensions. This 122 feet transferred over to here to allow us to subtract. Once we found this 157, it transferred down to here, again, to allow us to subtract dimensions. Let's see. Let's take a peek at something that looks like this. First. Pretend those are the same size. It's got a little crooked, but you guys get the picture. So I'm going to call this angle here 58 degrees. My two round pieces there are both going to have a diameter, I will call it 1.2 inches. Let's give us this dimension here is 2.1 inches. Just so that we have the significant digits, I'm going to do 2.100 inches. Let's do this dimension right here, 0.35 inches. Over here on the side, I don't need the dimension marker in there. I can just label that one. Let's go with .75 inches. And across here, oh, let's see here. We'll go with 7.5 inches across here. And from here to here, let's call that 1. I'll go 1.75 inches. So what I want to find here is the distance between my pieces of round stock there. This is actually a primitive clamp. You use round stock in V-grooves like that, so when you shove something between them, they push back into the V-grooves and they don't come out. So if we look at finding that dimension, I'll label that X here. We have a lot of things we need to find. First thing that we really need to know is we need to know the distance from this blue dot to that blue dot. So the distance between those blue dots can be found if I know this distance. Find that distance. I can use this triangle. Now I had to draw that in. This is a horizontal dimension. This is a vertical dimension, so I'm using that concept. I can find this angle because it has to be the complement of the 58 degrees. This is a right angle here. So 90 minus 58 gives us 32 degrees. So this is 32 degrees. I can also find this dimension here because I have the whole length here of the 3.75. I would subtract the 1.75 here. That puts me at 2 inches right now. And the 0.35 up here puts me at 1.65 inches is that dimension. I'm going to redraw that purple triangle over here, just to give us a little more space to work with it. We have 32 degrees here and 1.650 inches. What I need to find, the dimension I'm interested in, is this one up here. According to my 32 degrees, that's the opposite side. I have the 1.650, which is the adjacent side. When we're working with horizontal and vertical dimensions, typically what we will have is the opposite and the adjacent sides, which means we're going to end up working a lot with tangents. In construction, tangents are a very important trig function. All of our slopes and stuff like that deal with tangents. So here I will fill in, I know the angle is 32 degrees. The opposite side is what I'm looking for there. The adjacent side is the 1.65. So I make this a proportion, put it over 1, and I will cross, multiply, and divide. So tangent to 32 degrees. Make sure you close that parentheses before you multiply. Times 1.65 inches. Again, you don't really have to divide by 1, but I'll do it just to complete the problem. 1.031 inches is what we get there for that opposite side. This is 1.031 inches, which means if we subtract that from the 2.100 inches, that makes this dimension down here 1.069 inches. So that's 1.069 inches. This is 1.069 inches. Giving us that dimension between the blue dots, I'll just draw it in down here. That dimension is found by doing the 7.5 minus 1.069 and minus another 1.069. Now subtracting those, this is what, 2.138. So when we subtract that, we get 5.362 inches is that distance. From blue dot to blue dot. So now we need to get down to our dimension x here. To get down to that, we have to subtract pieces off of this 5.362. And the way those pieces are going to be set up, we'll have the center, the radius of the circle here, that dimension can be subtracted from each side. Of course, that's a 1.2 inch diameter circle. This is a 0.6 inch radius. So we need to know the distance from this blue dot over to the center of the circles. And to find that, I'll do it over here, it'll be less cluttered. To find that, I can cut this triangle. Now this triangle does two things. I have the radius of the circle to a tangent, that's my right angle. And then I connected the center of the circle to where two tangents intersect. That cuts this angle in half. So that was 58 degrees for the full angle. This angle is 29 degrees. So I'm going to redraw that triangle there. This angle is 29 degrees. That's my right angle. This side over here is 0.6. That is my radius of the circle. I am interested in this side. When we did the vertical V groove, we were interested in the hypotenuse. Here we are interested in this side, which is the adjacent side. And of course, the 0.6 is the opposite side. So once again, we are working with a tangent function. So tangent is equal to the opposite side divided by the adjacent side. The angle is 29 degrees, so it's tangent of 29 degrees equals the opposite side is 0.600. The adjacent side is what we're looking for this time. So we make it a proportion by putting the trig function over 1, and we cross, multiply, and divide. 1 times 0.6 is just 0.6, divided by the tangent of 29. 1.082 is that length. So this is 1.082 inches on both sides. So we have the 5.362. We're going to subtract 1.082 from each side. And we're going to subtract the radius of the circle of 0.6 from each side. Now let's see, I'm going to just add these together quick. So if I subtract that, I get 1.998 inches is the distance between them. So x here is 1.998 inches of space between those. What do you think? It's a lot of digging to find our missing triangles. And that is the part that is probably the most difficult part of any of these applications, is digging to find those missing triangles. Look at one that's even a little bit more complex. I'm gonna grab something quick so I get the numbers right on this. Every now and then, even I run into an example where I can't make up the numbers on the spot. So we have this dimension here. We're going to run this one in metric. We're going to do 47.39 centimeters. This dimension here, not drawn to scale, 92.37 centimeters. Our overall height, 306.08 centimeters. There's a radius here of 50.18 centimeters. What I want to find, and of course the distance from here to here, do it up top here. This distance here to here is 152.50 centimeters. The overall distance down here is 282.43 centimeters. What I want to find here is I want to find this angle here, angle X. To find that angle X, I can use the fact that that's a vertical dimension and this is a horizontal dimension. This is a right angle. So if I could find this angle, X is just going to be the complement of the purple angle there. Well, to find that purple angle, we've got a little bit of work to do. So I'm going to connect the center of this circle to that point there. And I'm going to draw from that circle, from that center, out to this point. That circle, arc of the circle comes around and it turns into a straight line. Where it goes from being curved to straight would be considered the point of tangency of where this straight line would touch that circle. So that forms a right angle if I draw that radius from the center of the circle out to where that goes from being curved to straight. Now this is a radius of 50.18, so that is 50.18 centimeters there. But right now, that's all I know about that triangle. I don't know anything else. I'm going to use this triangle. Now, if I had drawn this correctly, this center line would have been straight above that. There's a right triangle there. I know, first of all, one piece of that triangle is this dimension down here. It's the difference between these two. If I take 282.43 and I subtract 152.50, I get 129.93 centimeters. I also can find this distance here because I know from here to here is just a radius of a circle. That is 50.18 from there to there. I can subtract from the 306.08. The 306.08, I'm going to subtract the 47.39. Well, if I subtract that, I have 258.69. I'll subtract the 50.18, giving me 208.51, and then I'll subtract the 92.37, giving me 116.14. So this dimension here is 116.14 centimeters. I'm going to redraw that triangle. Put it in red here, this red triangle. So I have a little more space here. This is 116.14 centimeters. This is 129.93 centimeters. There are actually two pieces of information I want to know about this triangle. I want to know the length of that hypotenuse. I'm going to label that side C. And I want to know the length of this angle here. I'm going to call that angle theta. To find the angle, I have the opposite side and the adjacent side. So once again, I am dealing with a tangent. Tangent of an angle is opposite divided by adjacent. So I'll fill that in. I am still looking for the angle, so it's still tangent of theta. Opposite side is 116.14. The adjacent side is 129.93. So theta, my angle, the inverse tangent of 116.14 divided by 129.93. Second tangent, 116.14 divided by 129.93. Make sure I close my parentheses so the calculator knows what is inside that function. I get 41.79 degrees. So this is 41.79 degrees. So this angle here, again, it doesn't look like it, but it is 41.79 degrees. Obviously not drawn to scale. To find side C up here, it is simply a squared plus b squared equals c squared. I'll use the shortcut. It's the square root of 129.93 squared plus 116.14 squared. Second, square root 129.93 squared plus 116.14 squared. Close that parentheses. 174.27 centimeters. That's this right here. Now that I have those two dimensions, I can now look at this next triangle, this one here that I'll draw in green. I'll redraw that triangle down here. And what I know is I know that's the right angle there because that's where we intersected the tangent. This is my radius of 50.18 here. And this side here is the one I just found, the 174.27. And all I really want to know here is this angle. To find that angle, the 50.18 is the opposite side. The 174.27 is the hypotenuse. Sine is the function that deals with the opposite side and the hypotenuse. Of course, cosecant also deals with them, but that's a little bit more difficult to calculate on our calculator. So if I insert my information, I still don't know the angle, so I leave in theta for that. Opposite side is 50.18. Hypotenuse is 174.27. We are looking for the angle. So to just find the angle, we use the inverse trig function. So it's inverse sine of the 50.18 divided by 174.27. So second sine 50.18 divided by 174.27 gives us 16.735. Actually, just go 16.73 degrees. So up here, this is 16.73 degrees. So now let's look at finding angle X here. So if I look at that section there, that's a right angle. And I have two other angles coming off it. Here's my angle X. This one was the 16.73 degrees that we just found. This angle here was the 41.79 from over here. I'm going to combine those two angles to get an overall angle here. 16.73 plus 41.79 is 58.52 degrees. That's 58.52 degrees. So to find x, it is 90 minus 58.52, which is going to leave us with 31.48 degrees. That is angle x. That one's a mouthful. We have to draw in the appropriate lines. Once again, we were going from the center of a circle to a point of tangency. That was one of our strategies to get a right angle. And then we just did a horizontal and vertical intersection to get another triangle. But we had to build up. Here, we didn't use sides and then use an inverse trig function to find the angle. We actually found other angles than just subtracted to find that missing angle. That is the tough part in a lot of these application problems. Like I said, you got to find the triangles first. You got to draw in lines like we did here. But also then deciding, am I going to be fine, if I'm looking for an angle, am I going to find sides and then use those sides to find the angle with an inverse trig function? Or am I subtracting from other angles? The only way to get good at this is to practice. So, time to practice. We're going to give you a few pages out of the book, and we're going to give you some work time here. I realize we're working through the break here. And I'm going to give you about 35 or 40 minutes worth of work time here today. So this is out of the big book. In that big book, we have page 870 through 872, exercise 35-1, problem 7 through 21, the odd. Page 877 through 882. This is exercises 35-2. This one is 7 through 23, the odd. Then we also have page 888 through 891. This is exercise 35-3. And this will be 7 through 21, the odd again. Like I said, I realize we have quite a block of time. We actually have almost 40 minutes that I'm leaving you open here. These are tough. I fully expect that on Thursday, we may have to go over a few of these examples. So if you get hung up on one, spend a little time trying to figure it out, but then move on. The ones you can't figure out, we will come back on Thursday and work on. After this Thursday, we're going to be wrapping up our work with right triangles, and we're going to move on to what we call oblique triangles. They have no right angles in them. So that's what we're going to be moving on next week. Hopefully looking at getting to our unit test next week, Thursday. The reason I'm going to try to time that is next week, Thursday, I'm probably going to be, I've got some appointments I'm going to be wrapped up with, so hopefully we'll be able to schedule the test during that time so you guys can test while I am out of action. So with that, I will, if you guys want to start working on that, I will be on the network here for a while to answer any questions as they come up. Otherwise, you guys have a great day, and we'll